Hello, today we're going to be solving this integral in two different methods using Feynman's technique of integration. For the first method, we're going to do a u sub, where we let u equal ln of x. Therefore, the derivative of u is equal to 1 over x dx. And x is just equal to e to the power of u. So dx can be written as being equal to e to the u du. Now for the bounds of integration, as x approaches 1, u, or ln of 1, becomes 0. Now as x approaches 0, taking the limit as ln of u approaches 0, you get u being equal to negative infinity. So the new integral is from negative infinity to 0 of sine of u over u times e to the u du. After that, we're going to do another sub where we let z be equal to negative u. So dz becomes negative du. Inputting all of that, 0 remains 0, and negative infinity becomes positive infinity. And you have sine of negative z, that just becomes negative sine of z because sine is an odd function. Divided by negative z times e to the negative z, and again times negative dz. The negatives here cancel, and you're left with one negative here. This negative can then be used to switch the bounds of integration, and you get the integral from 0 to infinity of e to the negative z times sine z over z. With our new transformed integral, I set it as being equal to I, and I switched z from x to x because it was just a dummy variable anyways. Now, I we can set as being equal to a function of t and add a parameterized variable to the exponential function here. So we get e to the negative tx times sine x over x. And we can do this because at I of t equals 1, this just becomes our original integral. Another thing you can add is that as I of t approaches infinity, this whole thing will collapse to 0. This is because e to the negative infinity becomes 0, integrating 0 becomes 0. That's going to be important for later. And why did we create a variable for our integral? That is because you can take the derivative of this function as being equal to the derivative of the integral. And to take the derivative of an integral, you have to use Leibniz's rule of differentiation under the integral sign. This means that as long as this integrand is convergent within these bounds, you can take the partial derivative of the integrand. And so, with the partial derivative, that means x is basically considered to be a constant. It's not a variable as far as we're concerned. So, the only thing with the variable is this exponential function. We know that the derivative of e to the negative tx is just equal to, again, the exponential repeated times the derivative of the exponent, which becomes negative x. Writing this out, we have I prime of t is being equal to the integral from 0 to infinity of this x, and this x will cancel, so we're left with negative e to the negative tx times sine of x. And you can solve this using integration by parts, but a method I prefer is to use Euler's identity, which is saying e to the power of I times x is equal to cos x plus I times sine of x. This means you can take the imaginary part of e to the power of ix as being equal to sine of x. Transforming our function, we get I prime of t equal to the imaginary part of the integral from 0 to infinity, negative e to the negative tx times e to the ix. Then we can use the exponent laws to combine these two exponents. You can get e to the negative tx plus ix as your exponents. After that, you can factor out the negative x, you get t minus I. So we get e to the negative x times t minus I as our new integrand. Now, to solve this integral, we have the imaginary part of leaving the function alone and then dividing by the derivative of the exponent, which is negative t minus I. This is then evaluated as x approaches infinity and at x equals 0. For the first bound, we can evaluate as negative e to the power of negative x as x approaches infinity gets you 1 over infinity, which the entire first bound just becomes 0. Subtracting the second one, we get e to the power of 0, which is just 1. These negatives cancel out, and you're left with 1 over t minus I. From here, we get the imaginary part of negative 1 over t minus I. To get the imaginary out of the denominator, we multiply by the complex conjugate, which is just t plus I on the numerator and the denominator. In the denominator, we have t plus I times t minus I, which is just the difference of squares formula. This gives us t squared minus I squared, where the definition of I squared means it is equal to negative 1. T squared minus negative 1 is t squared plus 1. And we get that I prime of t is equal to the imaginary part of negative t minus I over t squared plus 1. Expanding this out, we get the imaginary part of negative t over t squared plus 1 minus I, or we can do plus I and then multiplied by negative 1 over t squared plus 1. This way you can more easily see that the imaginary part, or I prime of t, is equal to negative 1 over t squared plus 1. Now that we have a derivative of the function that represents our integral, we can again integrate this to give us I of t is equal to the integral of negative 1 over t squared plus 1 with respect to t. This is just the negative inverse tan of t plus c, because this is a definite integral, so we need to add a constant at the end. To solve for this constant, we take I of t as it approaches infinity, because we know that is just 0. This is then also equal to the limit, as t approaches infinity, of negative arctan of t plus c. The limit of a constant is just a constant, and the limit of arctan of t as it approaches infinity is pi over 2. So we get 0 being equal to negative pi over 2 plus c, which means c is just pi over 2. Then to get our target function, which is at t is equal to 1, because that becomes our original integral again, I of t equal to 1 is negative tan inverse of 1 plus pi over 2. So which gives us I, our original integral, being equal to negative pi over 4 plus pi over 2, which is just equal to pi over 4, which is the final solution of our integral. Thank you all for watching.